15 here, and 15 here. And my first question to you is, what direction does the system go? Okay? And I don't know is a really, really, really good answer for this one. Because I don't know either.
Oh, okay. Yeah, I was gonna say. Yeah.
All right? What this means is, I need to figure this out. All right? Oh, I didn't put in theta. You got to put. So how about we'll do a nice theta? Theta is 30 degrees. All right? So before I can answer a bunch of questions, there are some problem solving I need to do. But the first thing I'm going to do is called a free body diagram. And we're going to do 3 free body diagrams. The reason I'm doing 3 free body diagrams is because I have 3 different masses. And you do a free body diagram for each mass. So I have a free body diagram for M1. Free body diagram means I just draw a dot. And I apply all real forces to that dot. All the real forces on M1. There are 2 types of forces. What are the 2 types of forces? Field and contact. My field forces are the force due to gravity, the electric field, or the magnetic field on a moving charged particle. I have 3 fields that we're going to deal with within the AP1 and AP2, 3, and 4, because we're not going to deal with the strong nuclear force or the weak nuclear force, which is still electromagnetic anyway. All right, so 3 fields: gravity, electric, and magnetic. For right now, the only thing we're dealing with is a gravity field. So if you are on Earth, we have a gravity field where the little g is 9.8. If you are on Mars, we have a gravity field where little g is 3.4. If we are on the Moon, you have a little gravity field where little g is 1.6. So if you are on something that has a gravity field around it, there will be a weight. And weight is always straight down. So this is M1G. I will be saying that this is my expanded way is going to be this. And this is what I'll teach for AP1. It's what I asked for 3 and 4. It's the force due to gravity on M1 by the Earth. So I subscript and superscript your force. It's a force. The type is a force of gravity. It is on M1 by the Earth. The value of that force for my shortcutting for dealing with this problem as far as UIL is, it's M1G. That's what the force of gravity, that's what your weight is. Mass times gravity. All right. Since we're not dealing with electric fields or magnetic fields, that's it for field forces. All other forces must come from touching. If it ain't touching it, it ain't giving a force. So what's the only other thing touching M1? The string, right? So I have here, we'll call that a T1 and a T2 here. So I've got coming up here a T1, which I would say here would be a force of tension on M1 by string 1. But for now, it's just T1. All right, so let's look at M3 here. Free body diagram for M3. What are the forces on M3? Force due to gravity, so this is M3G. And tension, going straight up.
Attention, Mark Myers. I apologize for the interruption, but Willina Zarday, please meet your party out in front. Willina Zarday, please meet your party out front. Thank you.
Please, please, please. Tension. Tension is a really fun and wonderful force. Okay, so because he's not paying attention, I'm going to give it to him. Hold that. Okay, so I have a string here. All right, I want you to use the string. I want you to apply a force to me and push me that way. Push, come on, push me that way. Not very good at this, are you? That's all right, I wouldn't be either. What's the only direction he can apply a force to me? Oh, away from me. Y'all follow? And what direction is that tension? In the direction of the string. Move the string over there.
Looks like he's actually.
Now it's away from me in the direction of the string. Move it up. It's away from me in the direction. Y'all follow? It will always be away from the object, but only in the direction the string's going. So when you're doing tension, right, having a physical drawing is very important. Having the physical drawing here shows that, well, on this one, tension's just going up. So when I draw my free body diagram, it's just going up. Right? And we get a good one out of there. All right. Now comes the complicated one. M2. What are the forces on M2? What planet is it on?
Earth.
So I still get a nice M2G here. M2G. What else do we have?
T1.
T1, but isn't T1 going this way?
Yes.
And T2 is going that way? Anything else?
Theta, right?
Force normal. And what is force normal? Since you said something that not necessarily everybody has a definition of. What is force normal?
It's like what the object is sitting on and it like pushes back up.
Okay. When you have an object on a surface, the surface can provide two forces. The normal force is the perpendicular force. And so if I put the marker on the table, gravity's pulling down, but the table's pushing up. What do those two forces add to? Zero. Okay? So, Rachel, come here for a second. I'll use you. Using a girl because it makes more sense this way. Okay? I want you to imagine you're standing on a scale. Now, I'm not going to ask you for a number, okay? But you're standing on a scale. No, think about it, right? Don't you all get on scales every once in a while?
Yeah.
How many have ever been to the doctor's office? Okay, you've gotten on a scale. All right, so you're standing on a scale. Now, what is that scale going to read? I'm not asking a number, but what is that scale going to read in concept?
No, I'm joking.
It's going to read the weight?
Oh, the mass.
Okay. Well, if the scale has different numbers, it could read mass if it's in kilograms. It could read weight in pounds. Most of your doctor's offices, they say they read weight in pounds. Okay, so you're saying that it would read, if Rachel's standing on the scale, it reads her weight. I'm going to show you something magical, okay? Rachel just got fat. Okay? If I push down on her, wouldn't the scale read more?
Probably.
And if the scale's reading her weight, that means she just got fat. Obviously. And you can sit down. You're laughing too hard to do it. That's okay. Y'all follow that part though? If the scale reads your weight, and I push down on you, and now the scale's bigger number, and if it's reading your weight, you must get fat simply because I'm pushing down. Right? Now, what's the good part of that? It means if I lift up, you went on a diet. Instant diet. So does the scale read your weight?
No, for forces apply other forces and gravity.
Okay. Isn't the scale reading what the floor is pushing back?
Yes.
Because if I lift Rachel all the way off the floor doesn't have to put anything at all. It's going to read 0. So the scale is not reading your weight. The scale is reading the normal force. That make sense for everybody?
Yes.
That normal force is perpendicular. The other force the surface can do is frictional. The frictional force is parallel to the surface. So I have a normal. So my normal force is going to be going off in this direction. Force normal. And now I need a force of friction. What direction is the friction going to go? Ooh, that's a really good question.
I don't know.
Okay. If M3 wins, and this wants to slide up the incline, force of friction will be down the incline, because it's going to go against the intended motion. If M1 and M2 win, because doesn't M2 want to go down the incline? Right? So if M1 and M2 win and M3 goes up, well then the force of friction would be up the incline. So before I can answer that question, I still have to do some work. All right? Now, are these vectors friendly? What makes a friendly vector? Perpendicular or? Because the perpendicular vectors are just friendly. Right? If I have vectors going in the same direction, they are very, very friendly because you just add them. Vectors going in opposite direction are very friendly because you just subtract them. And vectors that are perpendicular, you Pythagorize. Well, aren't 3 out of the 4 friendly?
Yes.
So we just need to fix one. Which one are we fixing?
The one that's at the angle.
The one that's at what angle?
30 degrees.
What's that 30 degrees?
Well, T1 is at 30 degrees from the horizontal.
The one straight down.
How about we fix MG?
Yeah, okay.
Yes? Now here's why. What is the direction? What is the direction M2 is going to go? What are the 2 possible directions M2 goes?
Negative
Up the incline or
down.
down the incline. So the motion of M2 is along the incline. That needs to be one of my axes. The other axis is perpendicular to that. Y'all follow? So aren't these 2 and this one already in my axes? That's what I want. So I am going to break this up. Going that way and that way. Theta's up there. So this is M2G cosine theta, M2G sine theta. All right. Now, I want to know, what is M1G? I need a numerical value here. What is M1G? Five times 9.8. 49 newtons. What is M3G?
15 times 147.
Yeah, 3 times that. 147 newtons. All right. Isn't M2G sine theta the part that's pulling down the incline? Look at my M2G cosine theta. It's going like this. Is it going into the incline? Is it going to make it go down? No. So what is M2G sine theta?
Actually makes sense. 73.5?
I don't think so.
M2G says.
Oh, no, 15. I like. Yes. What is it?
Yeah, 73.5.
So 73.5 newtons. All right. Take a look at this problem. I have M1G wanting to make it go this way, right? I have M3G wanting to make it go that way. What does the 73.5 do? It wants to go this way. So aren't these 2 together?
Yes.
So what do these 2 together add to?
122.5.
What is it?
122.5.
122.5?
Attention, will Sherrod Taylor please
All right.
come to the main office?
So I have
Sherrod Taylor, to the
122.5
main
newtons.
office. Thank you.
Versus 147 newtons. If this was frictionless, who wins?
Down slope.
Doesn't 147 win?
Of course.
Bigger's winner, right? That means M3 goes down, M2 goes up the incline, and M1 goes up. If this was frictionless.
But it's not.
But I have a VUS and a VUK. So now we need to look at these for a second. Force of friction, I'm just going to give you the definition. Force of friction is mu times force normal. There's a static or kinetic, static or kinetic. When the 2 surfaces are not moving relative to each other, they are in a static situation. When the 2 surfaces are sliding, it's a kinetic situation. And you'll notice the static is always going to, the mu of static is always bigger than the mu of kinetic. Right? It's harder to get the box to start to slide than it is to just keep it sliding. How many have ever pushed a box across the floor? Right? You got to really push hard to get it started, but once you get it started, it's easier to keep it going. That's the mu-s and mu-k thing. All right? Now, force normal. What does force normal have to equal here?